Welcome to AI Paper Recap. Today, we're exploring an exciting research paper titled Using Code Generation to Solve Open Instances of Combinatorial Design Problems by Christopher D. Rosin. This study investigates how large language models, LLMs, can be leveraged to generate code that constructs combinatorial designs, solving previously unsolved instances of these complex mathematical problems. Combinatorial design problems involve arranging elements into structured patterns that follow specific constraints. These designs are widely used in many fields, such as experimental design, coding theory, network security, and even cryptography. Despite their importance, many instances of these problems remain unresolved due to their computational complexity. Traditional approaches rely on exhaustive search methods, optimization algorithms, and human intuition to find solutions. However, this study proposes a novel approach, using LLMs to generate code that constructs combinatorial designs, reducing the need for manual intervention. To achieve this, the author introduces a new framework called CPRO-1. The goal of CPRO-1 is to automate the process of solving combinatorial design problems by generating and executing code snippets that attempt to construct valid solutions. The framework follows a structured approach. Defining the problem. The LLM is first provided with a precise definition of a particular combinatorial design problem. This includes mathematical constraints and a description of the structure the solution must follow. Generating code. The LLM then generates Python code that attempts to construct a valid solution. It selects and implements different algorithms, such as heuristic methods, brute force approaches, and constraint satisfaction techniques. Verifying the output. A separate verification system is used to check whether the generated output meets the required constraints. If a solution is valid, it is recorded as a success. Iterative refinement. Since most code snippets will fail to produce a valid solution on the first attempt, CPRO-1 incorporates an iterative improvement process. The LLM continuously generates new code variations, adjusting parameters and algorithmic approaches based on prior failures. This approach allows the system to autonomously explore different techniques, leveraging both existing mathematical strategies and novel, AI-generated methodologies. Instead of relying on human researchers to manually test different algorithms, the system automates this process at scale, significantly increasing the chances of finding a valid solution. Why is this approach important? Traditional methods for solving combinatorial design problems often require extensive manual tuning and domain expertise. Researchers must carefully select the appropriate algorithm, fine-tune parameters, and experiment with different approaches. This process can take weeks or even months for particularly challenging problems. By contrast, CPRO-1 automates much of this process, allowing AI to explore and refine solutions without human intervention. Additionally, LLMs have the unique ability to generate creative problem-solving strategies that might not be immediately obvious to human researchers. By testing a wide variety of algorithmic approaches, some inspired by classical methods, others emerging from the AI's own reasoning, CPRO-1 can discover solutions that might have been overlooked. Results: success in solving previously unsolved problems. The effectiveness of CPRO-1 was tested on 16 different types of combinatorial design problems, including symmetric and skew weighing matrices, equidistant permutation arrays, packing arrays, balanced ternary designs, Florentine rectangles. Remarkably, CPRO-1 successfully solved open instances in 6 of these problem types, marking a significant breakthrough. To put this into perspective, These were problems that had previously remained unsolved despite the efforts of mathematicians and computer scientists. The AI, through its automated exploration, managed to construct valid solutions where traditional methods had failed. Let's take a closer look at some of these problems and how CP-RO1 approached them. The role of hyperparameter tuning and algorithmic diversity. One of the key strengths of CP-RO1 is its ability to explore multiple algorithmic approaches. Unlike traditional AI models that optimize within a fixed method, CP-RO1 dynamically generates code that tests different techniques, including heuristic-based search methods, for example, simulated annealing genetic algorithms, constraint satisfaction solvers that iteratively refine candidate solutions, brute force enumeration combined with smart pruning strategies to reduce search space. Additionally, CP-RO1 incorporates automated hyperparameter tuning, adjusting parameters dynamically based on prior results. This allows the system to optimize its search strategy without requiring manual intervention. Implications and future applications. The success of CP-RO1 opens new possibilities for the application of AI in mathematical problem solving. While this study focused on combinatorial design problems, similar AI-driven approaches could be extended to other domains, such as automated theorem proving, using AI to generate and verify mathematical proofs, optimization problems, applying AI to logistics, network design, and scheduling challenges, cryptographic design, exploring new secure encryption and error-correcting codes. Moreover, the ability of LLMs to generate structured executable code for mathematical problem-solving suggests exciting directions for AI-assisted research in numerous scientific disciplines. Challenges and limitations. Despite its success, the CP-RO1 approach has some limitations. High failure rate. The majority of generated code snippets fail, requiring extensive iteration. Computational cost. Running thousands of experiments demands significant computational resources. Limited interpretability. While CP-RO1 finds solutions, it doesn't always provide insights into why a particular approach worked. Addressing these challenges will be crucial for improving the efficiency and scalability of AI-driven combinatorial design. Final thoughts. This research represents an exciting step forward in the intersection of AI and mathematics. By using LLMs to generate and test code, CP-RO1 successfully solved multiple open instances of combinatorial design problems, demonstrating the potential of AI-driven approaches in problem solving. The broader implication is clear. AI is no longer just a tool for analyzing data or generating text. It can actively contribute to solving some of the most challenging mathematical problems that have puzzled researchers for years. That's it for today's AI paper recap. If you found this discussion interesting, be sure to subscribe, and hit the notification bell to stay updated on the latest breakthroughs in artificial intelligence. Let us know in the comments what you think about this approach and where else AI could be applied in mathematical problem solving. Until next time, keep exploring the world of AI